Okay, you guys, in this part of the lecture, I want to highlight Crimmins' methodology with a total synthesis. This will be quick. And this is the total synthesis of FD-891. Uh, it's a pretty overwhelming structure. It's a 16-membered ring macrolide, and it's been shown to have cytotoxic activity. Oh, you know what happened there? Against several tumor cell lines. And the synthesis, not surprisingly, is by Michael Crimmins, where he showcases his methodology. And he completed the synthesis in 2006 and reported it in JACS, volume 128. And it's a communication paper, so it's only 2 pages long. There is a lot of information in these 2 pages. So if you have questions, please come see me. But I'm not going to go through the entire synthesis. I'm going to try my very best to break down the molecule as much as I possibly can into very simple structures, to highlight certain parts of the molecule. So let me go ahead and start by first introducing what the molecule looks like and numbering as I go along. Let me go ahead and finish numbering it. And so you can see the 16-membered ring, 16 atom ring. There's an oxygen joining carbons 15 and carbon 1. And this is a macrolide. And I'll try to highlight this in a different color. You can see where Michael Crimmins uses his methodology. Some of it seems pretty obvious, some of it not so obvious. Okay. What I'll do is, what he did, excuse me, is he broke it into smaller pieces and then broke those molecules into even smaller pieces. And so I won't waste your time with everything. I'll just go ahead and introduce the small pieces, his target structures. So target number 1. And then target number 2. Let me first talk about target number one. You can see that target number one is specific to this area of the molecule. And target number two is actually starting materials for two parts of the molecule. It's for the carbon 15-16 part of the molecule and for the carbon 21 through 25 part of the molecule. Okay. And so that's why I haven't numbered target number two, because he uses it to synthesize both parts. But let me start off with target number one. And so he uses all commercially available starting materials. Just like I mentioned before, acylating is very similar to oxazolidinones. He treats his thiazolidine thione acylated system with titanium tetrachloride, spartine. And in this case, he uses an excess of it, so greater than 2.5 equivalents, followed by his commercially available aldehyde, which is an alpha beta unsaturated system. And because he's using an excess of his spartine base, he is going to see syn product. And specifically, he is going to see the dashed syn product. Which makes sense because the excess spartine is coordinating to the titanium, not letting the sulfur coordinate to the titanium, rotating around the way oxazolidinones rotate and going through the Zimmermann-Trexler transition state that we're so used to seeing. So you've got your syn product, but anti to your substituent on your thiazolidine thione. And so there is the precursor to my target structure number one. All I'm missing is the protecting group on my hydrogen, which is the same protecting group that I see at the end of my structure. Now, TBDMS stands for tert-butyl dimethyl silyl. Oh, excuse me, silyl. There are a number of protecting groups. There's an entire book on protecting group methodology in chemistry. Every protecting group has different volatility. They are specific to certain alcohols, whether they're primary or secondary, tertiary. They've got different ways of removing them. We've been used to seeing TMS, trimethyl silyl protecting groups. They're the most volatile. They're easy to remove. TBDMS is a little bulkier. It's a little harder to remove. You want it to stay there a little longer, protecting your alcohols. Luckily for us, you introduce protecting groups in a very similar way. And what I mean by that is you take your TBDMS chloride in the presence of an amine base and you protect your alcohol. And if you notice, the conditions are very similar to what we used for TMS in our previous lectures. And so there is target structure number 1. Okay. Let me move on to target structure number 2. And so just to remind you, please notice that in this case, the thiazolidine thione is on the right. We're used to seeing it on the left. So I'm just going to flip it around so that it's now on the left side, which means that if I flip it around, my stereochemistry inverts. It's not a reaction. I'm just flipping it around. Still the syn product, but my substituents are now wedged. Okay. So there's my target structure. I am starting with the exact same thiazolidine thione, where the benzyl group is wedged. So exactly the same thiazolidine thione that I used for target number 1. Please notice that in this case, it is the syn product, but it is now also syn to the substituent on my thiazolidine thione. So I still can use titanium tetrachloride as my Lewis acid. I can still use my spartine base, but now I'm only allowed to use one equivalent so that I can have coordination of my sulfur to the titanium. And I use my commercially available 3-butanol to get my desired product. Okay. And so I have what I need. If you notice, this is my target structure for 2 parts of the molecule. In this case, my OH is on the right and my methyl group's on the left. They're both wedged. If I flip it around, my OH group is dashed and my methyl group is dashed. And I've introduced the CH2 double bond, CH2 double bond. So I've been able to complete that part of the structure. Let me move on a little bit more to show you how they finish up or how they go on to focus on this tail end of the structure. The first thing that they do is they protect their alcohol, the DMS chloride with a base. And just with like other oxazolidinones, like I mentioned before, the way you remove them is exactly the same way. Lithium aluminum hydride, followed by water and PCC. They form the aldehyde. Oh, excuse me, I forgot to add the protecting group on my alcohol. And then they use the exact same thiazolidine thione. titanium tetrachloride, spartine, with an excess of base, 2.5 equivalents. And their aldehyde is the aldehyde that we just made. And so with the excess of base, we're going to get the syn products, and our syn product is going to be dashed because we're using that excess of base. And so there you've got your new syn products that are anti to the substituent on the thiazolidine thione. Please notice, excuse me, the dash followed by the wedge CH2. Please notice the dash followed by the wedged, the CH2, or excuse me, the CH. And so clearly, if you look at their paper, they continue on with the synthesis and functionalize the last tail end. But you've set the stereochemistry at the tail end already. It's really clever how they constructed the molecule. These three parts of the molecule were all used with Michael Crimmins methodology. Okay, you guys, I'll stop there with aldol chemistry. In our next lecture, I'll just finish off Dave McMillan's methodology. I'll introduce it. It's really short, it's really quick, it's really clever. He won the 2021 Nobel Prize in Chemistry. So I definitely want to introduce that so that you can see its importance and its relevance in organic chemistry. Okay, you guys.